Dithered transparency, also called screen door transparency, is an alternative to traditional alpha blended transparency that tries to use opaque rendering techniques while still sort of appearing transparent. In this tutorial, we'll explore how the two transparency methods differ and then implement dithered transparency using shader graph. Typically, it's cheap to render opaque objects because we just overwrite whatever color was previously in the frame buffer, and because opaque objects completely obscure other objects behind them, so we can skip rendering the hidden parts. To draw a transparent object though, we mix its color with the existing frame contents, using the alpha value of the new color to control the ratio between the two colors, hence alpha blended transparency. However, this transparency method suffers from sorting issues with complicated mesh shapes because sorting is done on a per object basis. This is where alpha clipping can help. Alpha clipping culls all pixels whose alpha falls below a threshold we specify, but we can still use it with opaque objects. Pixels are rendered fully opaque or not at all. By using a special dither pattern for those clipping thresholds, this one to be precise, we end up with a result whereby objects look decently transparent as long as your screen resolution is sufficiently high, but the object is still technically opaque. Those nasty transparency sorting issues are eliminated, and we might get a tiny performance boost too. Although some GPUs, especially mobiles, suck at alpha clipping, so you should profile if performance is a big concern for you. Time to jump into making the shader. Right-click in the project view and go to Create, Shader Graph, URP, Lit Shader Graph, and name it Dither Transparency or something similar. You can also follow the core bits of this tutorial with an unlit graph if you want. When you double-click to open it up, you'll see the output stack and the graph inspector. The first port of call is to head over to the Graph Settings tab and make sure, at the very least, that the alpha clipping box is ticked. This will add a new output block called alpha clip threshold, which will be very important for the effect we want to create. But of course, we can keep the surface type as opaque. Now let's add some graph properties. I'll start by adding a texture 2D called base texture and a color called base color. Together, these will control the albedo color of the object. Furthermore, they also control the alpha of the object. Essentially, if we want to modify the transparency of our object, we can change the alpha level of the base color property. I'll drag the base texture onto the graph and use a sample texture 2D node to sample its values, then multiply the RGBA result with the base color property. The output of that can be fed into the graph's base color output. Then we can use a split node to get just the alpha component of the color and feed that into the graph's alpha output. This will obviously be important in a bit. I'll explain what happens to the alpha very soon. Next, we're going to deal with most of the other graph outputs related to this being a lit shader. I touched on this in greater detail in my beginner shader graph tutorial series, so I will rush through some of these, but they're not directly relevant to the dithering transparency effect anyway. I'll add a new color property called emissive color and make sure to set its mode to HDR in the node settings. Then I'll drag it on the graph and connect it directly to the emission graph output. Next, I'll add a texture 2D property called normal texture, set its mode to normal map, then drag it onto the graph and use the sample texture 2D node to sample it, making sure to change the type to normal. After that, I'll connect the result to the graph's normal output. Then I'll add a texture 2D called metallic texture, drag it onto the graph, and use another sample texture 2D node to sample it. This time, since metallic textures are typically grayscale, I'll use the red output in the graph's metallic output. The ambient occlusion texture is pretty much the same story. Add the property, sample texture 2D, connect to the graph output. Next up, I'll add a texture 2D called roughness texture. I'll note here that the model I'm using comes with a roughness texture, but sometimes you'll get a smoothness texture instead, and they're essentially opposites. Drag it onto the graph and use a sample texture 2D node, but then feed the red channel into a 1- node to turn the roughness values into smoothness values. If you started with a smoothness texture, then you don't need the 1-. We can then use that in the graph's smoothness output. And finally, I'll add a height map texture property of type texture 2D and use a parallax mapping node to sample it. Then connect the output to the UV field of all the other sample texture 2D nodes we've used so far. Those are all the lighting related outputs dealt with, so now let's handle the final output, alpha clip threshold. Essentially, any pixel whose alpha is below the corresponding alpha clip threshold value is cold, which means it's not rendered. We have already dealt with the alpha output, and this is where it becomes relevant. For the threshold, I'm going to use a node called dither, which generates a repeating 4x4 grid pattern of values like this. When we reduce the alpha of the object, the pixels where the dither pattern is full white will disappear first, then the ones that are light grey, then the ones that are darker grey, and so on. The arrangement of the colours in the 4x4 dither pattern are what controls the order in which pixels disappear. Smart, right? Let's keep the infield as 1, as this controls the maximum value output by the node, then connects the output values to the alpha clip threshold. The dither node samples its values in screen space, so the last thing I want to do is add a float property called dither size, which I'll set to a default value of 1 and set its mode to integer. This property will allow us to modify the size of the dither pattern in case we want a chunkier grid pattern. Let's take a screen position node and divide it by our new dither size property, and use the result for the dither node's screen position input. And now the graph is complete. Returning to the scene view, we can see the results immediately by playing with the base color's alpha value. The dithered transparency effect always looks best when viewed at native resolution, so unfortunately, I imagine the combination of scaling the video plus compression looks less than ideal, but you can probably already see the kind of transparency effect in play here, as I can see what's behind the character mesh. As always, thanks for watching. If you learned something, consider subscribing or checking out my Patreon if you want early access to my tutorials. Until next time, have fun making shaders.